Today we're going to start an introduction to acids and bases, and then we're going to kind of dive in a little deeper after we do an introduction. So you may have an idea about what acids and bases are because you are exposed to them all the time, not just in chemistry lab, but at home as well. Something to note when you're going to recognize an acid or a base, most acids actually start with an H. So that's one way to tell that you have an acid. Most bases have an OH. Not all of them, but most of them do. It's actually the hydroxide ion, and actually the H in an acid is the H plus or hydrogen ion. Now, some examples of acids and bases. If we were in class together, I'd have you guys come up with some of these, but I want to show you in your reference tables, there's a table called Table K, and it has listed some common acids. When we look at these, you can see most of them start with an H. Their names are also given here, they're common names, but there's a couple that don't. So you can see here CO2, when it's aqueous, when it's dissolved in water, it becomes H2CO3. You can actually see the H2 and the extra O in there, the water, and that's carbonic acid. That's CO2 dissolved in water, which is the fizziness in pop, one of the reasons why your dentist doesn't want you to drink pop. Another one that can be kind of confusing because it doesn't always start with H is ethanoic acid. You may know it as acetic acid or the acid in vinegar. Because it's an organic acid, it may be written this way or it may be written this way. Okay, it has the acetate ion in it from your polyatomic ion table. So there's some examples of common acids. I also wanted to show you table L, which has some examples of common bases. We just said that they usually have an OH in them, and you can see that in the first three. Pretty obviously have the OH in them. This last one, though, the NH3, the ammonia, aqueous ammonia, is also a base, even though it doesn't have OH. And we'll talk about what that does to our definitions of acids and bases a little later. So we're just going to list a couple of these in our table here, or in our examples here. HNO3, that was an example of an acid. HCl, you use that a lot in lab. H3PO4, these are all acids. Also H2SO4, another one that you've used a lot in lab. And I'm just going to put here table K. And then for our bases, we have NaOH, KOH, and then I'm going to put NH3 aqueous. And those you can see in table L. All right, an operational definition is one that includes the observable properties, so things that you can actually see. So some things we know about acids. We know that they conduct electricity when dissolved in water. And we call that an electrolyte, if you remember when we talked about that in bonding. They react with most metals. When we test them against litmus, it turns litmus red. And if you were to taste them, and I don't suggest you taste anything in our labs, but they actually taste sour. If you look at your sour straws or your Sour Patch Kids, you'll see one of the first ingredients is citric acid, and that's what gives it its sour taste. Bases also conduct and are therefore electrolytes. They make water conduct. They don't react with metals, though. I need to move that a little more. That's unique to acids. They turn litmus blue. And I'll show you a little later on a table that'll help you remember that, but I always remember litmus is blue and a base. Blue and base both start with B, so it must be red in the acid. They turn another indicator called phenolphthalein, spelled super weird. They turn it pink. Normally it's colorless. It starts to turn pink at about a pH of 8. Bases don't have flavor necessarily, not that you would want to taste them, but they feel slippery, kind of like soap. In fact, soap is, or used to be made with lye, which is NaOH, which we listed up here as one of our bases. All right, so we've been talking about electrolytes, and what electrolytes do is they make water conduct. Remember that water would not normally conduct because it is a covalent substance, so they wouldn't conduct. These electrolytes, we now know, include acids, bases, and soluble salts, meaning that they actually dissolve. And don't forget, if you want to check to see if something's soluble, you can look in Table F. Acids and bases, when you add them to each other, will neutralize. If you add the same molarity and the same amounts, we'll talk more about that a little later on. And when they do, they actually produce salt and water. It's a special kind of double replacement reaction we call a neutralization reaction. And when you add an acid to a base or vice versa, you'll always end up with a salt, which is neutral, and water, which is also neutral. Now we're going to talk about conceptual definitions. These are based on theory. So theories in science have a basis of evidence behind them. It's not like the term theory you use in everyday life, like I have a theory that my neighbor's actually a serial killer. You know, there's no basis in fact or evidence for that. A theory actually has some evidence behind it. The first theory we're going to talk about, the Arrhenius theory, is one that we have since found evidence to prove isn't true. But it's the theory that's the most easy to understand acids and bases, and the one they actually ask about on the exam, and could use the name Arrhenius. What the Arrhenius theory said was that acids produce H pluses in solution. So when you add an acid to water, you're going to get H pluses. The Arrhenius theory says that bases produce OH minuses in solution. Oh, I said is solution. I meant in solution, which is only true if that base has an OH. And if you recall from a little earlier, we said that ammonia is actually a base. So ammonia is NH3. There's no OH in it in order to be producing those in solution. So that's why this is no longer the accepted theory, but it is the easiest theory to think of acids and bases. So down below I have HCl, which we know is an acid. It starts with an H. It's in table K. And we've put it in water. And when you do that, it actually dissociates or comes apart into the two ions that make it up, much like salts do. This is why it conducts just like salts do. And you're going to end up with those H plus ions, which is our acid ion, which makes it an acid according to the Arrhenius theory. On the other side here, we have NaOH, which we said is a common base. And when we dissolve it in water, it's going to dissociate into its two ions, which one happens to be the polyatomic ion hydroxide. That hydroxide ion is the base ion according to the Arrhenius theory. So that's what makes sodium hydroxide a base. Now we're going to talk about the Bronsted Lowry theory. On the exam, they don't use the name Bronsted Lowry, which I think is kind of silly since this is the current theory that's accepted. They call it the other theory. So if they bring up the other theory of acids and bases, this is the one they're talking about, our current theory, the Bronsted Lowry. And what Bronsted Lowry did in order to make it so that ammonia works as a base, they said that acids are proton donors. And a proton is essentially an H plus. Because hydrogen, a hydrogen atom, not a hydrogen ion, a hydrogen atom is just a proton and an electron. So when it becomes H plus, it loses that electron and is only a proton. So we say that acids are proton donors. So when you add them to a solution, they actually increase the concentration of H pluses. That's going to become important as we define bases. Bases are proton or H plus acceptors. So they actually pick up H pluses from solution. Water, just plain old water, H2O, can actually be written as H plus OH minus. And what will happen is these can dissociate from each other, and you'll have H pluses in solution. At neutral pH, you have the same amount of H pluses as OH minuses. What happens when you add a base to water is it'll actually pick up these H pluses, and it'll lower the H plus concentration. Bases don't have to have that OH minus ion according to the Bronsted Lowry theory, and that's what makes ammonia an example of a base, which we know it acts like a base. All right, now we're going to practice a little with this new information we have. HCl, is that an acid, base, or salt? Well, it starts with H. We can confirm because it is in table K, so that is an acid. Does that make it an electrolyte? Yes, it does. Do most metals react in HCl? When we look back at our operational definition on the front, you'll see that yes, it does. What color would litmus paper be? Not knowing how to read table M yet, you would look at your operational definition and see that it turns it red. And phenolphthalein is colorless or clear, and then it would taste sour. So all we're doing is kind of applying our operational definition to each of these. I'm going to do the next one with you as well, and then I'm going to ask you to fill that in yourself and check yours against mine when you're done. This is a base. It has OH, plus it's in table L. It is an electrolyte. Bases are electrolytes, but they don't react with metals. Litmus would be blue. It's blue in a base. Phenolphthalein turns pink in a base, and it feels slippery. I actually do want to do one more with you, but we're going to skip down to number 4. NABR doesn't start with H, and it does not have OH in it. It's not in table K, it's not in table L, but when I look at it, I can see that we have a metal bonded to a nonmetal, which makes it ionic. That makes this a salt. Are salts electrolytes? Well, as long as they dissolve, they do, and sodium being a group 1 metal, it will dissolve, or you could check table F. Metals wouldn't react with it, although they catalyze some oxidation reactions. The neutral color for litmus is red and blue together, which makes purple because salts are neutral. Phenolphthalein would still be clear, and it would taste salty. All right, so now go ahead and pause it and fill in the rest. All right, and then the last question, according to table J, which metals do not react in an acid? So we're going to look at table J now. So here's table J, and acids are actually represented by the H here. So remember that it would have to be, the metal would have to be more reactive than the H plus. So all of these metals would react in an acid, but the ones underneath would not. So the ones that don't react are copper, silver, and gold, which are actually our most precious metals. So copper, silver, and gold. And it's because they are less reactive than H2. Because H2 is the gas produced when metals react with an acid. And that's it.